So together with this kind of general concept solution process, and here in this section we will be specific and numerically how to solve for the three unknowns. And in these introductions of the general solution procedures, and we using delta E, and that is in specific for elliptic orbit. To make our solution general, so here we better to use X. We know the X defined that is universal variable, and whatever the value that can be corresponding to elliptic orbit, hyperbolic or parabolic. So these solution procedures, and right now again the first one that is the same we're using delta nu. Then here rather than using delta E or delta B or whatever, then we're using the universal variable X. Okay. So here we pick up this one, and the same concept, the same thinking like the step 1, 2, 3. We simply want to make a good guess and then improve. And so in this chance, and in this way, we will have the better way to write it up equations for, say, if using the Newton search method, then we will need to come up with the equation how to do the search and making the improvement. Everything in these sections will be to implement, focusing on how to improve this one. Then we can write it up the useful equations for this. Okay. And for the four equations, and in particular once we using the universal variables, we involve with the two particular function s and c. So here I rewrite here for the reference. So now the procedure is this. In a similar way, we make one guess, and here we guess. For that example, we guess delta E. So the same rule here we guess is the guess X. Okay, because the X can be related to those kind of eccentric anomaly we guess. And so say for our iteration, whatever iteration n indicating is n equal to 1, 2, 3, 4, 5, etc. And that is our progress of the guessing. And to calculate t, the time of flight. So see where I have, so let me use the same numbers, the same symbol here. So to calculate Tn, the same thing like we have before. In the step 2, we're going to calculate corresponding time of flight from the equation G. So to calculate Tn. And then we're going to compare Tn respect to our given time of flight, and whether is more than a tolerance. If not, then we go to the improvement. Okay, so basically here that is the general thinking process. And how to do it, let me summarize here. And right now I'm doing is follow up our textbook procedures. And if you have time to read our textbook, and the contents in this chapter is, I would say, for most of the textbooks in this kind of sections, the contents are formidable, which means involve a lot of these introductions, substitutions, and simplifications, etc. So here, hopefully this one can help you to ease. Hopefully you don't need to read the textbook, and then you can right away to write the programs here. So the strategy is this. And let me give the equation numbers, and right now I'm going to derive something useful. Let me go to equation 1, 2, 3, and give equation 4 here. So the strategy is this. So combine equation 1 and 2 via the universal variable x. Okay, so let me give you the result first, and then I will show you why. So in this way, we can have these useful equations. Y will be equal to R1 plus R2 and plus A times Z as minus 1 and square C. Okay, so here Y is defined as x equal to y over c, and A is defined by this. And so let me call this is equation 5. And the 2 are equation 6. Okay. And why we have this, and let me stop, and here is our scratch calculations. So again, this is a combinations into this, and right now I give you y. So from equation 1, equation 1, we have x variable on the right hand side. I simply move the remaining term to there. I express x in terms of other terms. So x variable in terms of that one is the square root of R1, R2 times 1 plus 1 minus cosine theta nu and P times C. Okay, and then we introduce it to equation 2. Okay, so once we have the expression of x in terms of this one, we simply introduce it to equation 2, and then we see what happened. So introduced into equation 2, basically you can see the left hand side will be the same, and the right hand side will be like this. And to save time, which will allow me to directly work on here. Okay, to save time. Okay. No. Okay. So here we simply introduce is x by whatever we have. That one is equal to R1, R2, and 1 minus cosine theta nu and PC. But you can, if you like, you can keep writing. And then once we have that one, then we simply, the next step is we simply, once we introduce the whole things here, we simply multiply the whole equations. I'm going to simplify the kind of basic terms. So simply I multiply R1, R2 with this equation on the both side, and I rearrange. And the rearrangement will come up with into this. Okay, so that rearrangement will come into this. So that one is equal to R1, R2. And so it won't be hard because everything here is algebraic, and you just pay a little bit of attention, probably a few more minutes, you'll get it done like this. So R1, R2 times 1 minus cosine theta nu P will be equal to R1 plus R2 plus R1, R2 sine theta nu and 1 minus cosine theta nu and Z as minus 1 divided by square C. Okay, so after we rearrange this kind of the result, and we got this one. So under this situation, again, this is a combination of equation 1 and 2. So here we simply define this is y. This is our y. Okay? And then this is our a. So basically here you can see we have y equal to r1 plus r2 plus a times z as minus 1 square c, and that is this term here, equation 5. Okay, why we do this one, because we want to save our writing and for symbolic expressions. Okay, so basically this is combination of equation 1 and 2. And so in this way, the y is equal to this, and also x equal to this. So we can simply easily to find out the x equal to this one, okay, as well. And also we calculate a is this one. And once we have this one, then we can have done is we can begin to calculate the associated time of flight. So right now we have utilized the two equations already. Then we're going to calculate the time of flight is from equation 3, because that appears here. Right? Okay, so right now we have the time of flight, and that one, time of flight, is equal to, by using x, that is what we define here, and using whatever we have, the time of flight is let me rearrange. Basically, I move this term to there, and so that is R1, R2 sine theta nu, and P, and plus x3 and s. Okay, so basically here, this one is for these terms. If you look at this carefully, this one is in terms of our defined variable, that is a times square y. Okay, so here I directly give you the summary from the textbook. So basically the time of flight, if you wish, you can put into here, that is mu and x3s plus a square y. And let me call this is equation 7. Okay, so right now we can compare the time of flight, delta t, and delta t we can compare with our given one. So I would say here, what would be the right way to use this? Hopefully you know this one is our calculated value. Okay, and this one is the symbol from our textbook. Sorry, the symbol from this equation. So hopefully you know what the meaning symbol here. Okay, so right now we have these equations. Then simply how to improve it. Our improvement basically is this. You know, if we are not good in this way, then we can have is this. We have a functions that is on your handouts here. Before we go over the handouts, you can see. So say to this step, if not everything good, so we can have the how to improve. For better xm plus 1. So that is from here. Usually is this, our thinking is this. We have our independent variables, and that is certain functions here. And that is the functions we, as in terms of the x. And our searching is this. So this is the root we're looking for. And right now is we are here, xn. Right? And by Newton's method is this. We can calculate this is the f of xn. And right now this is still have the certain distance. So basically we calculate the slope here. So this is the slope at f prime xn, right? So that means this is the improvement we can make. So here is our a xn plus 1. Graphically, the Newton's method is doing like this. So that means if there at that moment you are not satisfied with that result, then you simply get the two numbers ready. With the two numbers ready, then you can have your improvement that is simply this number divided by that number, and you got a little small step size jump toward your answers, and you keep jumping into that one. And how can we mathematically do this one? Basically, that is this xn plus 1 equal to xn. And this improvement is this. Okay, basically here we kind of graphically is moving backwards. So here our step size is moving backwards. So that's the reason why here is minus sign. And if I would draw the curve with a negative slope, then basically that would flip associatedly. Okay, so that is our program. And so basically I erase here. So here the improvement basically is to keep this is going. Okay, and what is the functions? So now we have the schematically mathematical program to here, but now we think about what is this function f. What kind of the function f we can use for this kind of gas? Again, we compare what? We compare is our time of flight. So the function should be using the time of flight functions. Okay, so the time of flight function is the time of flight function is the function of the x. Okay, so basically here I would say the time of flight is this. Let me erase this part here. So I would say where the functions is this. Where is the functions? So if you wish, you can define the function is okay, and this t is from question 7. Okay, so that means if you want to plug in, then we have is like this, the mu, and plug in that is we simply plug in here. So that is whatever, you don't need it. Okay. So by doing so, once we have come up with the x, and so that means for each iterations, I would say strategy here we have say n equal to 1, okay, and then let me put it to the things here. So when n equal to 1, let me put the index. So n equal to 1, then we can calculate z equal to the x. So z related to x. So basically here for each case, you need to update z. Okay, and then s is also a function of z. So you need to update s as well. So here, how can I do it correctly? So here, let me use the numbers here. So say if we start from here, So initially, in the concept, we need to start with the n equal to 1, then we calculate is, calculate Zn and S and C for Zn, right? Okay, Z and S are the functions, so whatever the Zn here, you do that one. So right now here we have the R1 and R2 are given. And what is A? A is this one. So A is the given constant. So A is the constant given. So basically to here, this should be fine. And then we calculate Y. So once we calculate Y, then we can, of course, here we can update the Tn. Because here the A is constant and n is our index iteration. Y is also our index iteration. So let me say this is the put into index here. So again, here I use color. That is to indicate we have an iterated value in each loop. So once we have in each one, then we have the each calculated here. So basically, at the end of this one, we have guaranteed we can always have a calculated time of flight we can compare. If not good, then we simply increase, not go to another iteration, say n equal to 2, then we read down everything here. Good? Right now to this point, and we have all the necessary information, very explicit information allow you, not me, to implement the programs. Okay, and hopefully you have learned enough experience with me in the past few lectures hours. I think I spent twice for the different programs. So hopefully you can develop this one on your own this time. Okay, and right now we still have, to this moment, this is the most important information we need to come up with. Okay, and that one basically is our search engine to how to get improvement. So once we have this done, everything else is a little bit trivial. But I still need to give other informations. So for example, here we have this function is given by this. Basically, this function involved with equation 7. We need to have, hopefully can give you the explicit form of the derivative. This one must be done manually in advance. And this one is done in our textbook. So here the df, dx, and that one is in our textbook, sections, equation 5.318 to 5.323. Okay, so that is equations. They kind of span a few pages, I think 1 or 2 pages, just in specific dedicated to these terms. Okay, and once that term is ready, then basically you're almost there and you can implement, except you need to come up with the initial guess. Again, the Newton's method always needs initial guess. So here we look at our handouts here. If you have a handouts, pretty much we can do it. How about this? We can do it next time. So next time I will try to complete the whole strategy, and by going over this handout, and then you have exactly the information for you to do the programming. And then next time, I think my goal is to use the programs I already have. We can look at for simple examples, please. Okay. So today we stop here.